Okay. This joint hearing of the Subcommittee on Space and Subcommittee on Research will come to order. Good morning. Welcome to today's joint hearing entitled Exoplanet Discoveries, Have We Found Other Earths? In front of you are packets containing the written testimony, biographies, and truth and testimony disclosures for today's witnesses. Before we get started, since this is a joint hearing involving two subcommittees, I want to explain how we will operate procedurally so all members understand how the question and answer period will be handled. As always, we will alternate between the majority and minority members. We will recognize those members present at the gavel in order of seniority on the full committee, and those coming in after the gavel will be recognized in order of arrival. And because of today's vote schedule, everybody, both minority and majority members, have decided we're going to submit our opening statements for the record, which will allow us to proceed directly to our witnesses' testimony. Now I'll introduce our panel of witnesses. Our first witness is Dr. Laurance Doyle, the Principal Investigator for the Center for the Study of Life in the Universe at the SETI Institute. Our second witness is Dr. John Grunsfeld, the Associate Administrator of the Science Mission Directorate at the National Aeronautics and Space Administration. And our final witness is Dr. James Ulvestad, the Director of the Division of Astronomical Sciences at the National Science Foundation. Previously, he was the Assistant Director of the National Radio Astronomy Observatory. He served in various capacities at the NASA Jet Propulsion Laboratory, where he played an important role in several interagency and international programs. As our witnesses should know, a spoken testimony is limited to 5 minutes each, after which members of the committee have 5 minutes each to ask questions. Your written testimony will be included in the record of the hearing. I now recognize our first witness, Dr. Doyle, for 5 minutes.
Thank you for inviting me. It's an honor to be here. My work in extrasolar planet research stretches back about 30 years, which is a decade before the first extrasolar planets were actually discovered. At that time, there were only two other people in the world working on the transit method, John Snyder and William Barucki, who's the PI of Kepler. The transit method involves the detection of a planet as it orbits in front of its star. In other words, one could say that one is detecting the shadow of the planet. Today, there are thousands of astrophysicists and their students working using the transit method to study and detect extrasolar planets. In the early years of this research, I was able to identify three methods for detecting extrasolar planets, and the 1990s directed an international network of telescopes to search for circumbinary planets. As a participating scientist with Kepler, I have been able to collaborate with the Eclipsing Binary Working Group in the discovery of several thousands of new eclipsing binaries. These are stars that orbit in front of each other, and if they're in the background of an extrasolar planet, they can look like the transit of a planet. So you have to catalog all the eclipsing binaries. My main work, though, as a participating scientist with Kepler has been the detection of circumbinary planets, that is, planets that orbit around two stars at the same time. This was discovered, the first transiting circumbinary planet was discovered in 2011, and it was called Kepler 16b. We began calling this planet Tatooine because of the Star Wars hero Luke Skywalker was watching a double sunset. And what we didn't know is someone called George Lucas and asked him if we could nickname it Tatooine, and he sent the director of Industrial Light and Magic to the NASA press conference. So basically, worldwide press picked up this as Tatooine discovered, but it was a great example of science fiction turning into science fact. And I like to think it had inspired many students worldwide to study math and science so they could turn science fiction into science themselves someday. In the context of the search for life in the universe, the Kepler mission has already made a huge contribution. At the SETI Institute, we have scientists working on all aspects of detection of life in the universe, including robotic landing missions and radio telescope searches. About 15 SETI Institute scientists are currently working on the Kepler mission. For about 50 years, SETI astronomers could only target stars. Now that Kepler has discovered the frequency of planets, we now can actually target planets that we know to be in the habitable zone of their stars. This is a huge step as far as the search for extraterrestrial intelligence. The next step in detecting life in the universe will be most likely to find biomarkers in the atmospheres of extrasolar planets. An example of this is oxygen, which is highly indicative of photosynthetic systems like forests, seaweed, microflora, and so on. Taking a remote spectra of the Earth, the detection of oxygen would be indicative of plant life, possibly animal life, and maybe even intelligent life. So it could be that the first detection of extraterrestrial life will be forests. Finally, to answer the question, that is the title of this session, have we found other Earths? We know that the best candidate to date is Kepler 62f, but it is also 1.4 times the Earth's radius. It may be slightly too big to recycle its atmosphere with plate tectonics, but we don't know for sure. A lot of modeling still has to take place. So I would say the safe answer to the question is almost. Within the next few years, Kepler will likely be able to detect exactly Earth-sized planets. To put this in perspective, 2,400 years ago, the ancient Greek philosopher Metrodorus of Chios wrote this: "To consider the Earth as the only populated world in infinite space is as absurd as to assert that in an entire field sown with millet, only one grain will grow." Within the next few years, we'll have the privilege of finding the actual answer to this age-old question: in the universe, is there another place like home? I think with the Kepler mission, we are just on the verge of answering yes.
I now recognize our next witness, Dr. Grunsfeld.
Mr. Chairman, members of the committee, thank you very much for the opportunity to appear before you today to discuss what I consider an incredibly exciting subject, extrasolar planets, as you've just heard, or exoplanets, which are defined as planets orbiting stars other than our own sun. As a young boy growing up in Chicago, I quite often laid on the grass at night looking up at the stars wondering, is anybody out there? And even explicitly, are there planets around any of those stars? This wonder about the universe and the question of whether there are exoplanets helped to drive me into a career in science and engineering, ultimately to become an astronaut and now the head of science at NASA. NASA plays a key leadership role in the quest to discover and characterize distant exoplanets and search for life in the universe. We work with a variety of space-based and ground-based telescopes, and in concert with the National Science Foundation and our international partners in observatories around the world. Since the first exoplanet discoveries in the 1990s, over 900 exoplanets have been discovered. There's an app on your smartphone you can check daily if you're really curious. And in just the last 4 years, the Kepler mission has contributed over 122 confirmed exoplanets and has over 2,700 candidates, most of which will probably turn out to be real exoplanets. Thanks to the Kepler mission, the statistics suggest that when you look up at the night sky, outside of the district, of course, because it's hard to see very many stars, virtually all of those stars have planets, at least one planet and perhaps a whole solar system around them. Even more exciting is the most common star in our galaxy, an M-class star. About 15%, or 1 in 6 of those stars, has a rocky planet in the habitable zone, and that's what Kepler has told us, if the statistics hold out more generally. The Kepler team recently announced the discovery of rocky planets a little bigger than the Earth around their host stars, and one of which, Kepler 69c, around a star very much like our own sun. The nearest habitable exoplanet, habitable meaning liquid water could exist on its surface, may be as close as 15 light years away. When the Hubble Space Telescope was launched, no exoplanets had been found, and we had 9 planets in our own solar system, now 8. Since then, the Hubble has not only directly imaged solar systems, one with 3 planets, but it's also measured the components of the atmosphere around one of those planets. Along with Kepler and Hubble, the Spitzer Space Telescope, the NASA Keck ground-based telescope in Hawaii, and many other ground-based telescopes are contributing to the rapid pace of discovery in this exciting field. In 2018, we will launch the James Webb Space Telescope, and that will give us a big leap in capability in our ability to study exoplanets. When we started designing the James Webb Space Telescope, again, we had not yet discovered any exoplanets. But its infrared capability, the fact that it has a coronagraph, and its ability to take the spectrum of the light from these exoplanets will really tell us a lot about the atmospheres and the components of those systems. But even before James Webb Space Telescope, we're going to launch the Transiting Exoplanet Survey Satellite, just selected as part of our Explorer program, and it's going to do an all-sky survey of the nearest and brightest stars, our neighbors, to see if there's transiting exoplanets around those stars. With the TESS information, we'll be able to target the James Webb Space Telescope, also the Atacama Large Millimeter Array, sponsored by the National Science Foundation, to really learn about these closest neighbors. All these telescopes will work together to answer the basic questions about these distant solar systems, determine the size of the planets, their mass, their characteristics, their atmosphere, their composition. Very exciting work ahead. Looking to the future, NASA funds technology development for exoplanet research and is studying the use of an existing telescope asset you may have heard about that we got from the National Reconnaissance Organization that will have a coronagraph that will be able to study the atmosphere of these distant planets in much more detail by direct imaging. We're also studying other techniques that will be infused into future telescopes that will be able to characterize an Earth-sized planet around a nearby star and search for evidence of life beyond our solar system. NASA is aware that exoplanets are of great interest to the public, the science community, and they bring together many scientific disciplines. That's one of the reasons why all of our data, from Hubble, Spitzer, Kepler, is all made available to the public. And this has resulted in an explosion of discoveries well beyond the NASA-funded research, including a number of discoveries by citizen scientists. In conclusion, NASA has a comprehensive program to detect and characterize exoplanets, and with the progress we've already made, I'm confident that it's not a question of whether or not we will find an Earth-like exoplanet, but when. With our programs, active participation of a rapidly growing scientific community, our partners, we will continue to make major strides forward in our understanding of the science of exoplanets. And programs like Kepler capture the imagination of everyday people. I think that's why you're all here, that you're also interested, including our students, who will be the scientists and engineers of tomorrow. NASA has exciting missions like the Hubble, the James Webb Space Telescope, TESS, and Kepler to reach even farther back in time to unravel the mysteries of the universe and to start characterizing and analyzing the atmospheres of exoplanets. The future of exoplanet research is bright, and NASA will continue to play a leadership role in that future. I look forward to your questions, and I have a very short comment, which is at the end of almost every public presentation I make, I have a quotation. And it's a quotation from Tennyson that I've editorially modified, and it says, "For I dipped into the future, far as human eyes could see, saw the vision of the new worlds and all the wonder that would be." Thank you very much.
I now recognize our final witness, Dr. Ulvestad.
Good morning, Chairman Palazzo and Chairman Bouchon, ranking members Edwards and Lipinski, and subcommittee members. Thank you for giving NSF the opportunity to speak to you today about our support of exoplanet research. So for millennia, people have looked up in the sky and wondered if there is other life out there, if there are other people out there. And determining if there were other planets around other stars was really something that couldn't be done for almost 400 years after Galileo first turned his telescope to the heavens. So when I was in graduate school at Maryland in the late 70s, early 80s, we never would have dreamed that we could be at the place we are now speaking about Earth-like planets. But just 20 years after the first detection of planets around other stars, we're now seriously talking about Earth-sized planets in the habitable zones of other solar systems, which I think is quite spectacular. So NSF has supported exoplanet research since its infancy. The first detections were made actually with NSF's Arecibo radio telescope in 1992, and it was very surprising to find planets around a compact star called a neutron star, which was not where people were looking. So I think exoplanet research over the 20 years since then has been full of surprises. Planets much, much bigger than Jupiter, very, very close to their stars. And these surprising outcomes have totally revamped the way we think about solar systems and the way planets form. So at NSF, the exoplanet research that we fund relies on three critical elements: investigators, that is people; tools, that is telescopes; and technology development. So we presently have more than 40 active awards to individual investigators who are doing exoplanet research, and many of these are people just beginning in our field. They're early career awards, they're postdoctoral fellowships, and this field is so exciting that a lot of the young people who are going into the field of astronomy actually want to work in this area. With our international partners, we provide the ground-based telescopes that complement the space-based telescopes that Dr. Grunsfeld has mentioned that are needed to make precision measurements of planetary systems. And third, and not to be neglected, we support technology development that is very important for getting us to the stage where we can detect planets as small as the Earth. For example, we support technology development that can be used to get more accurate wavelength standards that enable precision measurements of stars to determine motions that are being caused by planets with masses as low as the Earth. As exoplanet science enters its third decade, we're growing beyond just the counting of planets. Dr. Grunsfeld mentioned more than 800, 900 confirmed planets, but now we're funding research at NSF into characterizing planetary properties, into measuring exoplanet atmospheres, and into the formation and evolution of planetary systems. Starting next year, a new $25 million instrument on our Gemini telescope in the south will be used to image up to 600 other nearby stars. Trying to image planets, can't image planets right next to the star, but out at the distance of Jupiter and beyond. So over the last 4 years, NASA's Kepler satellite, as mentioned previously, has opened these wonderful new opportunities. And just to mention the complementary science, some of the recent discoveries have actually been made using Kepler data by investigators that NSF funds. We have an NSF early career investigator who helped develop the technique that was used to detect these two planets, Kepler 62e and f, that are thought to be in the habitable zone around Kepler 62. We are in the process of completing a very large instrument called the Atacama Large Millimeter Array, which was dedicated in Chile 2 months ago. And this, even in its pre-dedication phase, has detected the presence of Earth-mass planets around the bright star Fomalhaut, which you can see with your naked eye in the night sky just 25 light years away. And ALMA will in fact be incredibly complementary to the James Webb Space Telescope. James Webb in the near infrared, ALMA in the far infrared, both imaging dust shells and circumstellar disks around nearby stars at approximately the same resolution. As with all of NSF's major facilities, the data acquired with these instruments will be available to all investigators, not just to the people who propose to get the data. So one of the key goals of NSF's strategic plan is to transform the frontiers of science and engineering. And we think that since the very first exoplanet detections, NSF-funded research has transformed the frontiers of exoplanet research. And we will be very interested to see how the frontiers continue to be transformed over the next 20 years. Mr. Chairman, this concludes my remarks, and I'd be happy to answer any questions you and the subcommittee members might have.
I thank the witnesses for their testimony. Reminding members that committee rules limit questioning to 5 minutes. The chair will at this point open the round of questions. The chair recognizes himself for 5 minutes. Dr. Grunsfeld, the Space Telescope Science Institute indicated that a telescope larger than JWST is needed to detect biosignatures from terrestrial-like exoplanets. They also indicated that a heavy-lift launch vehicle, such as the Space Launch System, is needed to launch a telescope this size. How does the development of the SLS enable future exoplanet discoveries?
The Space Launch System, our large rocket in development, has the characteristics, of course, that it can lift heavy weights, but almost of equal importance for science is that it has a very large launch shroud. And so a future telescope that would have the light-gathering capability to detect and measure the biosigns, if you will, of a very, very dim planet around a very bright star will require a lot of collecting area and advanced instrumentation. And such a large telescope, if you think about how James Webb Space Telescope is going to launch, and I know, Chairman Smith, you've seen the model, that all gets folded up like origami and transformer into a launch shroud of an Ariane 5 rocket, very big. That's about the largest thing we can put into space in a conventional rocket. The Space Launch System is transformative, and this very large launch shroud would enable us to scale that up to something that would be a telescope that could detect life around a nearby Earth-like planet. We're looking very favorably on the development of SLS.
Also, Dr. Grunsfeld, how does NASA plan to manage education and public outreach related to exoplanet discoveries in the wake of the proposed reorganization of education and outreach funding? Are there any anticipated changes to the education and public outreach strategy? And how would the proposed reorganization impact the inspiration of the next generation of explorers?
Well, the first thing that I'll say is that the critical component in the inspiration of our next generation of explorers, scientists, engineers, and even more important, to have a very broad, educated populace in the scientific method and basic science, is to do exciting things that produces exciting scientific results that we can then get out into the public domain. You know, that's the number one requirement. And on that scale, we're changing nothing. NASA is going to continue working with NSF and the rest of the scientific community to try and make exciting discoveries. I think when we find a rocky planet around a nearby star that we think is very Earth-like, that's going to be incredibly exciting. And if we're so lucky to detect life on a planet like that, I think it will be transformative to humans here on Earth. As far as our NASA education, the President's FY14 proposal to consolidate the science, technology, engineering, and mathematics education infrastructure from a number of agencies into 3 primary agencies. NASA is part of that plan, and so our education activities will be transferred, and the budget with them will be transferred to a combined Department of Education, Smithsonian, and National Science Foundation architecture. That plan is still in development. Clearly, the administration has as its intention that this will strengthen the STEM education in our country. One of the things that I'm very proud of is that our science missions and the scientists who do that work spend time currently reaching out to master teachers, to pre-service and in-service teachers, and all the way through students. And so whatever plan emerges from this new reorganization, it's critical that we preserve that connection with the great science.
And my final question for Dr. Grunsfeld. The National Academy has issued their decadal survey, New Worlds, New Horizons, in 2010 that laid out the path forward for astronomy and astrophysics. How does NASA plan to adapt its plans for exoplanets now that we are facing a tougher budgetary environment?
Well, I did bring a graphic. I don't know if that's easily available to come up. But we have in our current portfolio of exoplanet research, and again, it's all done in concert with National Science Foundation, also private observatories, but we use ground-based observatories currently, Hubble, Spitzer, and Kepler, to investigate exoplanets. So that's our current stable of very powerful telescopes, and that's what's allowed us to make all this tremendous progress, as well as other ground-based observatories. The Transiting Exoplanet Survey satellite was selected out of our competitive program, but it does advance us quite significantly in exoplanet investigations in that it will find all of the closest transiting exoplanets. And that will allow us to use both ground-based and space-based observatories to start characterizing the nature of these planets, even down to measuring the atmospheres of the planets around these nearby stars. If we find something like an Earth, that will allow us to start looking for signs, even with James Webb Space Telescope, of water in the atmosphere. And if you have water in the atmosphere of a rocky planet in the habitable zone, that means there's probably lakes and clouds and precipitation. That gets us a long way towards that question of could there be life. Next, of course, is James Webb Space Telescope. The next 2 that are kind of dim are addressing what's in the New World's New Horizon. And so the first one is an astrophysics-focused telescope asset. That's just code for a study we're doing, which is to use the 2.4-meter optic system that we received from disposition of a National Reconnaissance Office asset. And we're looking at that as a wide-field telescope that meets the W-FIRST science requirements, and with the addition of a coronagraph, something that blocks out the light of the central star, would allow us to study nearby exoplanets in greater detail than we could have ever done with anything we have currently on the plate. Then beyond that, the New Worlds Telescope, that's just how it was described in the decadal survey, would be this very large telescope, something where the James Webb Space Telescope is 6.5-meter diameter, about 20 feet. In order to actually detect life signs, if they're there, of a planet around a relatively nearby star, we would probably have to go to 16 or 20 meters in diameter. And that's the one that was the reference in your Space Launch System question. And so we have studies going, technology work on prototype detectors for those future lines. Given the constrained physical environment, we're looking very closely at this NRO asset. as a way to bring down the cost of doing the next great astrophysics mission.
Thank you, Dr. Grunsfeld. I now recognize Ms. Edwards for 5 minutes.
Thank you very much, and thanks to our witnesses. I have to say the work that you do is among the most exciting that those of us who are lay people can think about. It truly is, and so thanks so much for everything that you do. Dr. Grunsfeld, I want to follow up with your last response, and it really does have to do with this constrained fiscal environment, because a number of the things that each of you has laid out requires an allocation of resources over a period of time for us to get this, get on with it, if you will. And so I wonder if you can tell me how the current budget environment is really affecting exoplanet research and the additional technologies that are going to be needed over this next decade, and what are the likely impacts if we should continue with sequester into fiscal year 2014?
So there's no question that the budget environment has caused us to have to make some tough choices. And whenever we try and make those tough choices, we think about balance, we think about scientific priorities. And in the case of exoplanets, we're very fortunate that we have high-value observatories on orbit. And so one of the things we have to prioritize is, what are we going to keep operating on orbit that are providing high scientific return? The latitude we have for adjusting to a changing budget is really in the start of new projects. And so as an example, even though we have selected the transiting exoplanet survey satellite tests, we've had to start to slow the start of that mission by about 6 months in just what we've seen from this year and looking into FY14. If we continue into a sequestered environment, then we're going to have to look at perhaps turning off an operating observatory or cutting back further on the development of new missions. And something like the study for the NRO Asset Telescope, AFTA, we would have to reduce our investment in that future, which would, of course, slow that down further. Now, that's a study. We haven't approved or come to you to ask for approval either. That's not approved internally within NASA or externally. We're just looking at the feasibility right now on that. But it would slow down future development.
Dr. Ulvestad?
Yeah, I'd say there's two primary issues that we would have to think about in terms of the constrained fiscal environment. One is that some of the new observatories that I spoke about are more expensive to operate than the older observatories that we used to have. And so in a constrained environment, in order to operate those new tools, what sometimes has to give in the short term is the research grants to individual investigators. And as an example, I'll cite the ALMA telescope, which we're just bringing online, which we expect to be used very strongly in conjunction with JWST. So I'll just mention that's actually one of the ways that we will maximize the science is by trying to have these space and ground assets work together on coordinated programs. But one of the issues that we will run into is that ALMA, which is an international telescope, if we're not able to fund our investigators to do the research and to bring their postdocs and graduate students in, some of the best exoplanet science with that telescope might be done by our international partners and not by the U.S. investigators. So I think that's a very serious concern for us. The concern other than that is just being able to make sure that having invested lots of money in these big tools, that we're able to operate them adequately, that we don't start doing things like scrimping on the infrastructure because we're trying to save a little bit of money here and there, and then essentially causing damage to the big investments we've already made.
Well, let me follow that up because it's one of the concerns I've had, for example, with James Webb Space Telescope, is that we actually got, a lot of extended lifespan out of the Hubble because a lot of upgrades were made over a period of time. And so that gave us a tremendous bang for the buck. But the question is whether, if we face future delays, that, into 2018, will we beyond then be able to get more bang for the buck out of JWST in the same way that we did out of Hubble?
Quite a long time ago, we looked at making the James Webb Space Telescope serviceable, similar to the Hubble. And largely due to the fact that it's an infrared telescope and it has to be very, very cold. Its design was to put it 1 million miles away from Earth, and that's a very inaccessible place. And so we abandoned the idea of visiting it and upgrading it. So the James Webb Space Telescope doesn't have the capability for upgrades the way Hubble does. So what determines the James Webb Space Telescope lifetime is really the onboard fuel. And so we've designed it to a design requirement of 5 years. But that's with, being NASA, we have redundancy, we have reserves, we plan for failures and operations. We hope, and actually the engineering says, we should get 11 years of life out of the James Webb Space Telescope in an actual operational mode that we think we'll use. Given that framing, we're looking very closely, and I'm very excited about the partnership with observatories like the Atacama Large Millimeter Array, because that's the way we're going to maximize the output of the James Webb Space Telescope, is by using our other assets. I have a little bit of a dream, but that dream is that not only will we have the ALMA and the James Webb Space Telescope, that we'll also have some overlap with the Hubble Space Telescope. And engineering mechanics will determine that lifetime, but right now Hubble is still doing well.
I now recognize Mr. Bouchon for 5 minutes.
Thank you, Mr. Chairman. Over here. I'm going to make a comment first, and then a couple of questions. This is not the only hearing that we've heard from people who depend on discretionary, so-called discretionary spending at the federal level. And my comment is that until the American people can help us address the entire piece of the federal spending pie, of which 60% we're not addressing today in Washington, D.C., people who depend on discretionary spending are continually feel the pinch, which is problematic, as Ms. Edwards pointed out. At this point, there's really only one significant proposal in Washington, D.C. to address the 60% of the pie, and that's on our side of the aisle in our budget. Until the American people help us address that, we're going to continue to have ongoing discretionary funding problems, because most of the driver of our national debt is not in discretionary programs, it's in mandatory spending. And everyone in D.C. recognizes that as a major issue. The question I have, first question I have is, I guess any one of you can address it, and I think it's important when people like me go back to Indiana and talk to people about where we spend money and why. And so, Dr. Grunsfeld, in a short order, what can I tell people why what you're doing is important to the American people?
Well, there are a couple of different levels, but I'll try and keep it short. The first is that investments in NASA and the National Science Foundation in basic research is really the investment in our future, and it's not an abstract thing. Vannevar Bush and the Endless Frontier, the document that helped spur on the creation of the National Science Foundation, really cued it up as, our investments in basic science are what are critical to our economic prosperity, our health care, and the future of the country. And it's just a wonderful document to read, because that's coming out of World War II, and the question was asked, how did science help us win the war and then generate such a strong economy? If we start cutting back on the basic research, on trying to solve very hard problems, like how to build the instruments on James Webb Space Telescope that challenge our industry, that challenge our engineers, that allow these companies to grow new techniques and new competitive tools, we'll just continue to start losing ground on the kinds of innovations that drive our economy. And that's a very tight loop and well-documented loop. At the other end of the extreme is this idea of kids looking up in the night sky, and I think we've all done that. And the science tells us things that just inspire us, that cause us to want to look towards the future, to have vision, that drives people through hard times, and that makes it into the science textbooks that hopefully our students then bring with them as they become future decision makers in our country, not just in Congress, but as medical doctors, and most importantly, as parents of children, that they have the knowledge to make good decisions based on technical knowledge. Thank you. Okay,
I assume everyone's going to have a similar response, because I have another question that I want to ask. By the way, I agree with you. I think that when I talk to people about NASA, and this comes up all the time, I pull out the list of things that have been developed technologically and innovations that have come through NASA that aren't just about putting a person flying around the Earth and going to the moon, but all the other things that have happened as a result of developing the technology to make that occur. My second question is, I'm always interested when I see, and I hate to focus on NASA, but like our project that on Mars, is that we're looking for water, we're looking for carbon-based life forms, and there are other, that's our definition of life, so to speak. Are there people out there that have other definitions of life that are looking into that we might also be exploring for?
Well, I think that that's a good question for Dr. Doyle from the SETI
Sure,
Institute.
that'd be great.
I will say that the Curiosity rover, although it has the scientific instruments, the mass spectrometers, to look at all the components of the soil we're digging up and looking for some signs of perhaps previous carbon stuff going on, it would see many other things. But I'll pass that to Dr. Doyle.
I'll just say the definition, some of the people working in the field of exobiology are looking at the definition of life as anything that can store information. So there's a broad brush there. So there are studies going on about a broader definition. Right now you have to work with what you know, but silicon-based information storage and crystals and so on has not been out of the realm of consideration.
Okay, thank you. I yield back.
I now recognize Mr. Lipinski for 5 minutes.
Thank you, Mr. Chairman. I just want to start out by asking Dr. Grunsfeld about the status of the decision on what to do with the telescopes donated by NRO. You had mentioned them, but has that all been determined? What is going to be done with those?
So the answer is no, we haven't determined what's going to be done with those. That's the subject I was talking about of the astrophysics large focus telescope asset that we've done a study on. At the end of this month, I'll get the results of that study, and then we'll brief Administrator Bolden, and that would allow us to go to the next step from just the study phase to actually, if he approves it, seeing if we should start doing some engineering to validate that those telescopes could actually be used for a future space telescope. Right now our focus is on completing the James Webb Space Telescope. As we get further into the development of that telescope, then we could start seriously thinking about building another mission of some kind, whether in astrophysics or another area. We're very excited about what we're seeing so far, and I'm happy once Charlie Bolden, our administrator, has dispositioned it to come back and talk to you about it.
Very good. I want to ask all the panelists, what, if anything, is needed to further facilitate the coordination and collaboration between NSF and NASA on exoplanet exploration and research? Is there anything more that would help? Any places for improvement that you see?
Well, let me at least start with that. I think that, as you heard from our testimony, we understand very well how our different assets could work together with each other, and we're in pretty regular communication about setting up joint programs and so on. In fact, I think one of the key elements is actually even working at a lower level, which is that our program officers in the two agencies actually talk to each other regularly. We had a meeting of all of our program officers in our Astronomical Sciences Division and in NASA's Astrophysics Division about a month and a half ago, just to talk about making sure that we kept our lines of communication open, making sure that we understood which proposals we were getting and they were getting for research, so that we were doing complementary things and not doing duplicative research. So I think that was a very important aspect of our coordination, is to maximize the efficiency of the funding. I would say that it's not clear to me that we need a lot of help as long as we keep talking to each other, which we're doing very regularly right now. So I'll yield to Dr. Grunsfeld, see what he would like to say about that.
I would concur on that. I think one of the I wouldn't take this too far, but I think one of the effects of always being budget limited for research in space astronomy and ground-based astronomy is that you're forced to be very communicative and creative with your partners to make sure that you don't have duplication, because there isn't enough money to be able to duplicate things. In the case of the National Science Foundation and the NASA efforts in exoplanets, it's a very nice division because we use basically the space-based and ground-based as the first natural breakpoint.
Thank you.
I would just say that SETI Institute's a nonprofit, and there are many research institutions that are rather small, but they've started up support of exoplanet research. For example, Planet Hunters has millions of people that go home at night and start looking for planets. So there's this huge upswell of millions of supporters of exoplanet research that is also in kind of the nonprofit realm as well that could be tapped.
So always good to hear. I know we have a lot of members here in a short time, so I'll yield back the rest of my time. Thank you.
I now recognize Chairman Smith for 5 minutes.
Thank you, Mr. Chairman. Actually, my first question, I think, has largely been answered, and it was how do we expedite the process of searching for exoplanets? And it sounds to me like we need to stay on track with the exoplanet missions that Dr. Grunsfeld, you highlighted a while ago. Would you all agree, Dr. Doyle and Dr. Grunsfeld, that the first thing we need to do is make sure the current missions that have been proposed are funded, and not all have been funded? Would that be your recommendation?
Well, I'm glad to say that.
Or are there any other missions that we ought to consider?
Yeah. So I agree with you completely. The plan we have is I think the best plan that we could have, and that the administration's proposal for FY14 funds us to go on with the next mission, which is the Transiting Exoplanet Survey mission, and fully funds James Webb Space Telescope. All of that said, ultimately nature will determine when we find the first planet that looks just like Earth.
And Dr. Doyle, are there any other missions we should be considering other than the ones that need to be funded?
Well, I think the ones currently are quite well planned to do an all-around survey, and then to follow through with detecting exo life, basically.
Okay.
So I think we're on track.
Good. Dr. Grunsfeld, I was going to point out, I think when you quoted Alfred Lord Tennyson, you didn't realize that we had the quote that you mentioned on the wall behind the podium, or did you notice that?
I noticed that in 2003 when I was chief scientist, and that's when I started putting it into my talk.
Oh, is that right? Good, that we came first. As you know, it's a long poem, and that's a refrain that's repeated throughout the poem, so it really has a good impact. Dr. Ulvestad, you mentioned our international friends and the missions that they have initiated. Do you think we should perhaps duplicate some of those missions, or should we rely upon information that we get from them?
Well, I think that what we're doing right now with our international colleagues is we're not doing duplication. We're actually going in together to build one telescope that any one of us would find it difficult to afford by ourselves.
So that's mutually beneficial.
So I think that's mutually beneficial. An example, again, we keep coming back to the Atacama Large Millimeter Array, but originally there were concepts for a similar telescope in Japan, in Europe, and in the United States. 3 different telescopes that were all going to end up fairly close to each other in Chile. And rather than building those 3 separate telescopes by the 3 areas of the world coming together, we were able to build one much more capable telescope that we all can use.
Okay, thank you. Let me ask you all this final question, and that is that what new technology do we need to develop in order to expedite the process of detecting organic life on an exoplanet? And do we need to do more than we're doing? And if so, what do we need to do? And when do you expect us to have that blockbuster news that there is possible life on another planet? Dr. Doyle?
Well, of course, as mentioned, you need a much larger telescope, but the detection of oxygen would be definitely an indicator of life on another planet. If it transits, you can also, that's another method for detecting oxygen on an exoplanet. But
do we have the technology now to detect oxygen on another planet?
If there was a very close star, like an M star, in a very close orbit, and we got lots of transits and we could differentially subtract, we might be able to squeeze by and get an oxygen line or so. Okay. But the next mission, of course, is to get the nearby transiting planets,
right.
And then we could consider it. Like Dr. Grunsfeld said, nature is the one that will decide whether we can do that in the near future.
Dr. Grunsfeld, anything more we should be doing to expedite that time?
A critical limitation is really the ability to separate the light from a bright star from the light from a very dim planet next to it that's in reflected light. And so we're spending a fair amount of technology funds and researchers working on techniques to do that light suppression across a broad variety of fronts, 4 or 5 different techniques. And so we're making a lot of progress. I think within 5 years, we will have demonstrated that if we put one of those instruments on a new large telescope, we would be able to detect essentially signs of life if they were as obvious as they are on Earth.
Okay, we're going to hold that to you within 5 years. Or
we'll have the technology. Yeah,
Okay.
you can hold me to that.
Okay, Dr. Ulvestad, any more thoughts on that?
I think the key that Dr. Grunsfeld just referred to is really being able to separate the light of a dim planet, which a planet like Earth is dim when it's many light years away, from the light of the very bright star that's its host. And so, for instance, the instrument I mentioned on our Gemini telescope is one of the steps along the way, but I also mentioned that it could only detect planets that were out farther than Jupiter, which is not where we expect Earth planets to be. So we've still got a ways to go to be able to null the star down to the dimness we require.
Thank you all for your testimony. Thank you, Mr. Chairman.
I now recognize Ms. Bonamici for 5 minutes.
Thank you very much, Mr. Chairman and Ranking Member, for this interesting hearing, and thank you to the witnesses for your expertise. I'm going to ask 2 questions together because of the interest of time, hoping that each witness can respond to each. We've also had discussions in this committee about near-Earth objects and the potential for asteroid incidents. And in those hearings, we talked a lot about international collaboration because obviously this is not just an issue that affects our country. So will you each discuss briefly the nature of international collaboration in the exoplanet research? And then the second question has to do with more of a big picture issue. As members of this committee, we're privileged to be frequently presented with this extensive information on these issues and hear from people with expertise. And then when we're back in our districts, we often find that the public at large lacks specific information about the work that NASA is doing and, importantly, how it affects them. So with that in mind, could you also address how you publicize what you're doing, how you educate the public about not only the discovery of exoplanets, but how to best translate that into the benefits to the public at large? Thank you. And I'll ask each of you to respond to those 2 issues.
I'll go ahead and start. Almost everything we do in NASA has large international collaboration. The International Space Station, the James Webb Space Telescope, these are partnerships where there's integral collaboration between European Space Agency, Canadian Space Agency, the United States, in the case of the space station, Russia and Japan, and these are working great. I would say probably 90% of everything in the Science Mission Directorate is an international collaboration at some level, where we are contributing to a leadership of a European instrument, or another country is contributing to leadership in one of our programs. James Webb Space Telescope is an example where the U.S. is leading. Even on the Hubble Space Telescope, originally that it was a 15% share of European Space Agency, but when we actually go to use the telescope, it's very broad. And of course, all of our data is public, and so anyone can actually use it, and so that's much further. When we discover things, we put them out as press releases, we put them on websites, but more importantly, we have an education and public outreach program where the scientists work with master teachers, and that gets into the curriculum materials, into the textbooks, and into pre-service and in-service teachers who then work with millions of students. That's how we work through the educational side. Through more informal education, we reach out to libraries across the country, planetariums and museums. We do exhibits and shows, and all of that contributes to the public knowledge of the science benefits from NASA.
Thank you. Dr. Doyle?
On the Kepler team, I would say we have a huge number of countries represented. There's the Astrobiology Consortium, which is centered in Denmark, but there are 500 members of that, and that's just a spin-off from the main Kepler science team. So I would say Kepler is automatically international. With regard to reaching out and educational activities, one of the things that we're doing is basically starting a series of kind of a wiki university where people can learn about life in the universe from the SETI Institute and take classes and so on, and I don't see any reason why they couldn't pass the SAT after taking our classes. So it's free and online, and let's go for it.
Thank you. Dr. Ulvestad?
Yeah, first on the international front, like NASA, most of our major activities now are international in terms of building big telescopes and operating big telescopes. But I will honestly say that there is also some competition there. In the use of those telescopes, we would like the scientists from the United States to actually be leading in the discoveries. So they may be in collaborations, in fact often are, with other international scientists, but we do want to make sure that the U.S. scientists have the opportunities to use the tools we've built. Now, you mentioned near-Earth objects, so I'll just pick up on that for a second. The #1 ranking in the National Academy Decadal Survey for a ground-based instrument was actually something called the Large Synoptic Survey Telescope, and one of its science goals is to characterize the asteroid population in our own solar system, and can do that very extensively, including near-Earth asteroids. That happens to be not an international partnership, but a partnership with the Department of Energy. So you may consider them international relative to NSF and NASA. They have slightly different cultures than we have, but that's a different sort of incredibly valuable partnership. With respect to the public information, one of the requirements we have at NSF for everybody who applies for a research grant and for our large facility managers is something called broader impacts. And they're required to tell us what they're doing, will do in their grant for broader impacts to the public. So in getting ready for this hearing, I was actually looking at the research grants that we've been making on exoplanets over the last several years. And a large fraction of those people, their broader impacts involved going into high schools. It ranged between K to 12, but high schools seemed to be a particular point that they were interested in. And that, if I can pick up on a previous question, is very important because...
I'm sorry, my time has expired.
Thank you, Dr. Ulvestad. I now recognize Mr. Robacher for a couple minutes. Not the full 5.
Couple minutes. Let me just note that we've been engaged in a search for intelligent life for a long time over in the Senate, however, and sometimes it's hard to determine. Just want to make sure we understand that the at last mission concept does not necessarily rely on the SLS rocket, does it not? There are other 2 proposed architectures for this system that would not require us to build this big booster. That instead could be launched on EELV class launch vehicles. Isn't that correct?
Yes. So the Advanced Large Area Space Telescope concept is one of these New Worlds type future large telescopes. And in that study, there were 3 telescopes studied, an 8-meter diameter, 9.2.
Well, the answer is yes. I got
Sorry, the answer is yes. And
the answer is yes. So
yes.
This is not an. Do you know what the budget for the SLS launch system is? We don't know, so you don't know either. Quite frankly, that was a leading question.
All right.
And if that money was going to be taken out of your budget to develop the SLS launch system, rather than go with the launch systems that we've already got, would you be supportive of that?
No.
Right. I just want to make sure these are on the record because there's a lot of people pushing for the SLS launch system. We don't even know what the budget is. We don't know where the money's coming from. And it's really possible if we do that, we'll just defund all the things the SLS is supposed to carry, meaning your projects.
Yeah.
Last thing is Arecibo telescope. I noticed that the NSF Arecibo Telescope Observatory was actually the ones who found the first evidence of this exoplanet. Let me just note, we almost closed that down for lack of funds, and some of us understood just how important that was. And let's make sure we, because that telescope remains a very important part of the very projects that we're talking about. So, Mr. Chairman, thank you very much for the hearing, and I just wanted to make sure we got on the record. Thank you.
I want to thank the witnesses for their valuable testimony and the members for their questions. The members of the committee may have additional questions for you, and we will ask you to respond to those in writing. The record will remain open for 2 weeks for additional comments and written questions from members. The witnesses are excused, and this hearing is adjourned.